Hey everybody, welcome to the 3.4 notes. This is about differentiating inverse trig functions. So we're going to connect inverses and trig, and it's going to be amazing. So just a reminder, the derivative of sine of x is cosine of x. But the question is, what is the derivative of the inverse of sine? Another way that you might see that written is arc sine of x. So that is another way to say the inverse of sine. So if you ever see like arc cosine or arc tangent, know that it's asking you for the inverse. So it's another way to say it. And so there's a bunch of rules that I'm going to give you in a little bit that you can memorize. But I want to show you real quick how these rules are being found, so you don't believe that we're just pulling it out of thin air, just to make some connections. And so this exercise we're about to do is just going to take some prior knowledge, some skills that you learned in previous classes about trig. So try your best here. So basically, this is the equation. So we want to find the derivative of the inverse of sine. Okay, y equals sine inverse of x, but we don't know how to do that yet. So I'm trying to think, are there ways that I could do this without knowing the rules? And this is going to take a long time. Obviously, we're going to learn rules and it'll go by quicker, but I'm going to try to figure out, is there an equivalent expression that I could determine to figure this out? And so just in the same way that you can like balance equations and add 4 on each side, I can also, the way that I get rid of an inverse sign is by signing the inverse sign. So I'm going to do sine of y and basically like signing both sides. I'm taking the sine of both sides. So this stays as sine of y, but these are inverses of each other, and so that gets me down to x. And so now I have an expression that's more familiar that I actually can take the derivative of with implicit differentiation. So I'm going to take the derivative of both sides. And that will give me cosine of y times dy dx equals 1, and then if I solve for dy dx, I get 1 over cosine of y. So that is the derivative of the inverse of sine, but it's in terms of y, and we started in terms of x, and so we need to finish in terms of x. And so this is going to be kind of crazy, but just hold on for a second, okay? So we're going to do some skills that I would say probably mostly geometry skills. I don't know when you would have touched it next, but we're being told from here, going over here, that sine of y equals x. And so what does that like really mean, right? So just to refresh your brain, at some point in probably geometry, you could have been told something like sine of 30 degrees equals 1/2, right? And that you could use the unit circle to figure that out, but also that's kind of a geometry skill. Remember, if you're looking at a right triangle, it's SOHCAHTOA, and sine, tangent, and cosine are just ratios of side lengths of a triangle. So sine is just the opposite over hypotenuse if you're worried about the angle. So for example, in this degree, sine of 30 degrees equals 1/2. I'm plugging in 30 for y, and x is our ratio. If I had a right triangle, here's my right angle. Say this is 30 degrees. Well, I'm being told that the opposite is 1, and then the hypotenuse is 2, and that coincides with the idea of SOHCAHTOA, and that's that, okay? But let's think about this like in a more general sense, because we don't know what y is in this situation. We don't know what x is. Well, in this situation over here, what was plugged in for y was the angle measure. So let's just pretend I'm going to draw a better triangle. Let's just pretend our angle measure is going to be y. And then sine would mean if it's opposite of our hypotenuse, then I would have to be getting like x over 1 for it to simplify to 1. So the opposite side is x and the hypotenuse side is y. Well, down here, I want to figure out what cosine of y is. So to do cosine of y, I would do adjacent over hypotenuse, but notice I don't know what the adjacent side is. So I'm just going to, for a second, just put a variable there. I'll just use a. And I want to solve for a in terms of x because my final answer needs to have an x in it. So what I'm going to do is I'm just going to use the Pythagorean theorem. So a squared plus x squared equals 1. And then I'm going to solve for a. So I'm going to subtract x squared on both sides. I'll get 1 minus x squared. And then I'll take the square root of both sides, and that will give me a equals plus or minus 1 minus x squared. But because I've been working all with positives, I'm just going to take the positive. So I get that a equals the square root of 1 minus x squared. Therefore, cosine of y equals adjacent, which is 1 minus x squared, all over hypotenuse, which is 1. So I'll get cosine of y equals 1 minus x squared. And so if I come back over here to my derivative, that means that the derivative of my inverse, which was 1 over cosine y, is also 1 over 1 minus x squared. And that is so to recap, I'll put this in my box down here. That means that the derivative of inverse sine equals 1 over 1 minus x squared. And so you will not be asked to do this on the AP test or anything like that, but I just wanted to show you that we're not making this up. It's coming from something. And so if you want to see more of that, I'm sure you go on Khan Academy and look for more proofs. This is a proof of these equations, but this is how they're getting them. And so from here, I'm just going to tell you the derivative rules. So we just talked about how the derivative of the inverse sine is 1 over 1 minus x squared. Technically, there are 6 trig derivatives because there's sine, cosine, tangent, but there's also cotangent, secant, and cosecant. But the 3 other ones are not used as much on the AP test, and so I figured that we might as well just focus on the 3 that are used more frequently, just to not confuse you guys too much. But so the derivative of the inverse of sine is 1 over 1 minus x squared. The derivative of cosine, you can kind of guess this, but remember the derivative of sine is positive cosine and the derivative of cosine is negative sine. So this is what is the same as the derivative of the inverse sine, but it's just the negative version, which that's like kind of easy to memorize. And then tangent is going to be 1 over 1 plus x squared. So notice that that's a plus sign, and then there's no square root here. So the difference is you're going to see a 1, a 1, a 1, a 1, a 1, a 1, an x squared, an x squared, an x squared, but the sine and cosine ones have square roots. They have negatives. The cosine one is negative, and then the tangent one has a plus sign and no square root. And if you wanted to figure out how all of those were found, you could do the same exercise we did as above. So maybe try to do that. It would be fun. So now let's just do some problems with this, okay? And you might have to scroll up and down, maybe Google them so they're all in one place. But this first one says find the derivative of arctangent of x cubed. So remember what I said, arctangent is another way to say the inverse. And so this is a composite function, okay? The outside is arctangent and the inside is x cubed. So I'm going to start by taking the derivative of the outside, and the derivative of the outside is going to be 1 over 1 plus blank squared, okay? And then we're going to plug the inside in, which is x cubed. So that's like the inside function part, right? And then we're going to times it by the derivative of the inside, which is going to be 3x squared. And then I will clean this up, and I will get 3x squared all over 1 plus x to the 6th power. And that is the derivative of arctangent x cubed. So deriving it's kind of complicated, but everything from there is just like, you have to use the chain rule, so that's not always fun, but it's like pretty similar, pretty standard to everything else we've been doing. So hopefully, besides the memorization, this isn't adding too much stress. Okay, next problem. If, this is a funny notation, so we'll see how you guys feel about this. Okay, if g of x equals the derivative, if g of x equals inverse sine x over 2, then the limit as x approaches 3 of g of x minus g of the square root of 3 all over x minus 3, x minus square root of 3 is what? You're like, where did this come back? The reason I put this on here is because I want you to recognize that this just means find the derivative at the square root of 3. This is the derivative notation, so this just means find the derivative at the square root of 3, okay? So that's all it's saying, and you don't really need to do it the long way. You can use our new techniques, but you need to be able to recognize what that's asking for. If it's asking you for the limit of a difference quotient, which this is a difference quotient, then it's asking you for the derivative at whatever they're plugging in for x. So to do this, I'm going to ignore the at 3 part first, and I'm just going to find the derivative part. And so this is going to be 1 over, it's again a composite function, 1 over the square root of 1 minus x divided by 2 squared times the derivative of x over 2, which is just 1/2. So that's going to give me, when I clean it up, 1/2 1 minus x squared over 4. And now I want to find that at the square root of 3. So I'll have 1 over 2 square root 1 minus square root of 3 squared all over 4, which simplifies to 1 over 2, 1 minus 9/4. And yeah, let's just keep going. It'll be fun. Wait, this is wrong. This should be 3/4. 1 over 2, 1/4, which equals 1 over 2 times 1/2, which equals 1. Amazing. Feel free to check my math and make sure I did that correctly, but I think I did. Okay, one more problem, right? Oh, 2 more problems. Sorry, guys. Okay, so this one says, if arc cosine 3 of x equals the natural log of y, then dy dx. Well, this is kind of a brutal problem because we have an inside and an outside function. And over here, we have an inside and an outside function, but also it's not solved for y. So we're gonna have to use all of our things. We're gonna have to use the chain rule, implicit differentiation, and our new arc tangent, our inverse rules. So arc cosine is the same as saying the inverse of cosine. So I'm gonna do that part over here. So this is gonna be 1 over 1 minus 3x squared times 3. And then over here, so I don't have to use implicit differentiation on that side, but over here I do. So it's going to be 1 over y times dy dx. And then I just have to solve for dy dx. So really, this is not that bad. I'm going to just simplify this before I move over anything. So this will be 1 minus 9x squared equals 1 over y times dy dx. And then I just, I'm going to multiply y on both sides to get this y to cancel out. And I will get 3y all over 1 minus 9x squared equals dy dx. And I'm all done. It really wasn't that bad. Okay, now last problem. If you have any questions, let me know. Okay, so arc sine of negative 4x. So all of these problems are always going to be composite. Just be prepared for that. So this will be 1 over 1 minus, so dy dx is, use my notation, negative 4x squared times negative 4. It simplifies to negative 4 over 1 minus 16x squared. And then I want to find it at x equals negative 1/6. So that'll be negative 4 over 1 minus 16 negative 1/6 squared, which is negative 4 1 minus 16 times 1 over 36. Ooh. Just doing some computation here, which that will equal, this is equivalent to 36 over 36, so that will equal negative 4 over 20 over 36. Shall we keep going, or do you guys want to stop? We'll just keep going. I'm going to simplify the fraction first, so that'll be 5/6, right? Divide both of those by 4. Yeah, we can just stop there. That's probably good enough. Okay. Oh, wait, there's one more problem. I'm so sorry. I thought we were done. Okay, one more problem. Last one. Shouldn't be too bad. Arc tangent is going to be, the derivative of this is going to be dy dx equals 1 over 1 plus 2x squared times 2, which is 2 times 1 plus 4x squared. And then I want to figure that out at negative 2. So I'm just going to plug in negative 2 squared, and I'll get 2 over 1 plus 16, which equals 2 over 17. If we made any mistakes, let me know, but I think we did great. So that's all it is. So the deriving it is hard, but after that, it's pretty standard problems. So have fun. See you later.